Oh, okay, it's working. Cool. Hey, so Brant Bucher, who's on the CPython core engineering team, has submitted this interesting pull request on Christmas Day, I think, for a JIT compiler for CPython. So I wanted to have a look at this and see if I can get it working. There is a talk he's included in the comment in the PR, where he kind of explains a few bits and pieces about this, but it's always nice to see these things in real life up and working. So that's what I wanted to do just quickly, is to show you, I guess, a bit what this thing is, how it works, and try and use it. This is a draft pull request. It is not finished. I think there's still some things to do in the review. There's a lot of people very interested in this. I think there's a lot of expectations about what this will be and what it will do. So I hopefully get to debunk some of that just quickly. So as with everything on GitHub, you can copy that link there and you can clone the branch. So I've got a copy of this already. This is a feature for CPython. So when you run configure, you'll need to give it an extra flag, which is enable experimental JIT, which is this one here. So if you turn that on, then that will enable this experimental feature. So if you're familiar with JITs, I guess it's a general term, but it could mean a lot of different things. So in this case, it is a special type of JIT called a copy and patch JIT. If you've never heard of that, you're not alone. I'd never heard of this either. There's a paper associated with it, but it's actually quite a simple concept. The concept is that you sort of compile a program and then you leave gaps in the program, and then you patch in the values at runtime for the addresses of specific things or some variables or some data or stuff like that. So what this means in CPython's case is basically it JIT compiles part of the interpreter specifically for your function or for your code. This is a foundation pull request, I think, that will basically lead into a lot of opportunities for optimization in the future. I've had a look at this and kind of looked at how it's doing it, and I'd be surprised if it was any faster than CPython currently, and I wouldn't be surprised if it was slower. But that doesn't mean that it's not worth it, because I think how this works basically opens up the opportunity to JIT compile part of CPython code, your function objects, away from what they are at the moment, which is opcodes interpreted at runtime, and actually JIT compile those into machine instructions. So let's have a look at it anyway and see what's going on here. Now, first place you want to go is in the tools folder. There's a new directory called JIT, and there's a README in here. You're going to need LLVM 16, which is a very new version. You'll need that for Linux, Mac, and Windows, and there's some instructions on how to get hold of that. Oh yeah, Happy New Year, by the way. So there's some instructions on how to install that. I installed it using Homebrew because I'm using Mac. Now, some important things to note. LLVM is not required by the person running Python. It's required by the person compiling CPython from source, which is not your average user. And it's required because it uses, this new JIT uses LLVM to compile these templates, basically. And the way this copy and patch JIT works is it creates a whole bunch of mini programs. It compiles them using the LLVM compiler, and then it compiles them, and then it like disassembles them and turns them into header files. So it's a bit weird. I mean, the idea is brilliant because bundling a JIT and CPython would be a huge shift away from how CPython currently works. You'd have to bundle the actual compiler in CPython. You'd have the compilation overhead as well, which would be big. If you look at every alternative to CPython that runs Python and has a JIT. All of them have an overhead for the initial compilation stage, and CPython is probably one of the quickest at the initial compile. So like there are JITs for Python, and this one is a bit different. So basically what you'll find is there's this tool folder, and once you run configure with so you want to do enable experimental JIT, and then also do with PyDebug, so you get all the debug stuff. I've done that already, so I'm not going to run that again. And then the other thing you can do is to make with 4 cores and then quietly, and that's going to run a new make job. This new make job runs a Python script called build. This build script basically generates the JIT stencils, and it does that because there's been some other changes to CPython separate to this PR that it's a bit that's quite interesting. So what they're trying to do with the interpreter is the interpreter used to be this huge big loop in CEval. Where is it? The interpreter used to be this massive big loop that basically loops through a compiled function. It keeps changing, and I used to know this file really well, but I don't know anymore. It's completely changed. Yeah, I'm just fumbling in the dark now. Okay, that used to be a huge big for loop that used to loop over every instruction in every opcode in a function, and then like run the corresponding C function. So like I've got an example here, like this test function, for example, like takes an argument x, assigns a variable I to 0 while I is less than x, I plus equals 1. So like that compiles down to, let's open up a REPL. If you import the dist module and do dist.dist test func, that compiles, because Python is a compiled interpreter. It compiles not to machine code, it compiles to these little instructions called opcodes, bytecodes. Each one of those codes basically corresponds to a set of instructions in C. Like load const means load constant, that's the number, that's 0, I guess. Yeah, that's the 0 on the right hand side of that operation. So what the eval loop will do is basically go through each of these instructions in the function when you call the function, and then like load values, store values, call functions. That's kind of the heart of how CPython works. There's been some changes recently to CEval. Used to be this kind of big loop with a case statement, with a switch statement saying, okay, if it's load const, then do these things. If it's store fast, then do these things. And what the developers on CPython wanted to do is that those instructions are really, really generic. So like, for example, the binary op. So plus equals, the left hand and the right hand side of that operation could be anything. Like I could be a string, the right hand side could be none. Like it is not specialized at all, and so the binary op, in fact binary op is not even specific to plus equals, it's just a generic binary operation. Binary operation is just an operation that takes two parts with the left hand side and the right hand side. So what they've done is to basically create a whole bunch of specialized opcodes, which is the specialized adaptive interpreter that was part of CPython 3.11. What's happening in 3.13 is they're then breaking these opcodes into even smaller parts called uops or micro-ops. And these uops are basically much smaller instructions. So if you've ever looked at other compiled languages that have a JIT, they typically use, like Java has this, .NET has this. There's like a level, there's like a level beneath the compiled code called the IL, and this is like a very low level language that's not quite machine code. It's slightly abstracted from that, but it's somewhere in between the two. So it's basically a really convenient way of writing something like machine code, but it's not platform specific, because you still want this to compile and run on different CPU architectures and different operating systems. So we've got this test function. Now, what the JIT does is basically it takes these new UOps and these operations, and what used to be a big switch statement is now actually generated. So this CEVAL, like the new interpreter loop, is actually generated at compile time for CPython. And they've got a whole bunch of new opcodes, UOps as well. So like the load fast instruction, for example, takes which variable in the frame are you loading, load it, add a reference count to it, and then add it to the stack. So like that's quite simple. This code is now generated by a build script. That's important because it actually relates to the JIT as well. So what's happening with this JIT is, as far as I understand it, I've only just looked at it, and it was just the code was only kind of released like last week. But from what I understand, basically they want to be able to effectively turn like this function, and instead of having a loop that has to read each opcode, to basically like copy out the C instructions for that opcode and then write them into a mini program. That's kind of what's happening. Now, what that looks like in Brant's PR is he's got this build script. This build script generates a JIT stencils file. So what's happening in the build script is that you've got these kind of mini programs, which is, here's the instructions to handle a load fast instruction, for example, which is you take the op-arg, you take the local, and you increment the reference count. Now, what Brant was saying is that, okay, instead of getting the op-arg and getting, like, if we know at compile time that the arg for load fast for this instruction, which is load the variable I, we know that arg is 1. So we know it's trying to load the first local variable in that frame. So therefore, kind of replace that with the number 1, and that means you can kind of propagate that. So what the JIT is doing, it's kind of a JIT, but it's not a JIT in the way that I think of them, which is IL-based JITs, I guess, that are generating machine code on the fly. It's basically writing these mini programs and compiling these mini programs. And it's done that by, first of all, taking these executor cases and then basically compiling each one of them into a template. And that template is then written into JIT stencils. So, for example, let's go and look at an easy one. I say easy, we're looking at assembly code, so that's not really the right word. Okay, load fast is really the easiest instruction there is. So if you were to turn load fast into a program, then this build script basically uses LLVM to compile a program for the right architecture. So my machine, that is Mac OS 64-bit Intel CPU. I'm not on one of the new fancy ones. So that would be the target. It would be Mac O. That's the binary format that Macs use. And he's got some instructions here about how to compile that program, basically. And at build time, and again, build means the build of CPython, sounds like it's JITting the interpreter, not the Python code. Yes, kind of. That was a question in the chat. Could you up your audio levels, maybe? Sorry. Let me remember how to do that. that might work. So CPython will, at build time of build a CPython, it will basically run this build script. And for each of these executive cases, it will turn this into like a mini program, compile that program, and then disassemble it, and then basically leave some instructions about what things need to change at runtime. And this is the important part, because if you compile this into a binary, then the linker replaces some important stuff in here. Actually, so for example, pi_number_ is a function that is in part of the Python binary. The address of that in the binary is decided when you statically compile the CPython binary. So like the C compiler and then the linker basically says, okay, the address of that function is this. The issue is that if you, with JIT compilation, one of the issues is you basically got to like figure out what the addresses of these things are. So how this JIT works is they create these stencils, and this is the assembly code for this particular stencil, and you'll see some breadcrumbs that might be easy to recognize, I guess. So for example, here you've got PyIncref. So like that calls the increment reference count on that particular object. You've also got like the oparg. So that is something else that needs to be written in. What this JIT does is it creates this stencils header, and it describes these things called holes. And the holes are basically like zeros that were written into the assembly, like the machine code. So this is the machine code. This is a disassembled version of that as a comment, so you can kind of read it and understand sort of vaguely what's happening. And then there's basically a list of holes that need to be filled. And for example, the load fast one, because that's really easy to understand, you need to provide the oparg. You need to provide the address of that function. I haven't quite worked out what these other ones are yet, but the important ones seem to be replace the 0 value at instruction counter 39. So that was, where was that? Here. Okay, so we had in here was the instruction 39 saying that should be the address of incref total. So what the JIT does, at runtime, it uses this new optimizer interface that's in CPython. And the way that works is you've got these executors or executors, I don't know which way you want to pronounce it. And at interpretation, it will decide to basically, it can optimize certain bits of Python code. And it's kind of a pluggable interface. It's designed, and this is one of the first implementations that uses this new API. But I can see how other developers not in CPython, but like for other projects, could possibly hook into this. So the example I wanted to kind of show you was this test function. This test function will actually be JITted, and I've got like just a script that I wrote to like see what's happening here. The thing I don't understand yet is why. I'll get to this in a minute, but the executor, the one with the JIT code, is like the last instruction, the jump backwards. I don't know why that is, and that's also in the test case. Like this function is in the test that Brant submitted as well. So when you run that function, like with an argument with this new JIT enabled, it will basically compile the stencils, and it will compile the stencils together and store that into memory. So it basically like writes out those bytes which are the machine code instructions for this mini program. It also then replaces or fills, I guess, the holes that are left in with the runtime arguments. And that's all done in this new JIT.c file. So that basically like goes through and fills the holes. So you see the hole kind. So patch, which is the bit that gets filling the holes. So go through each of the hole kinds and replace it with whatever the value is supposed to be. So a lot of these are actually to do with like the address of something, like a function or like a type or something like that. You've also got like the simpler ones like the oparg and stuff like that. So yeah, what it will do is basically copy that compiled code. So this is basically a set of machine code instructions. It fills the holes to write the addresses, and then it writes that into memory. And then when you call that code, it will basically like get the JIT code address, which is how JITs work. You basically write the machine code to RAM, you put it in memory space, you tell the operating system that that's okay to execute that memory, and then you basically just call it. So basically that's what it does, is it creates a machine code instructions at runtime, and it calls that at runtime. So yeah, so Tushar asked, is how will these machine codes be optimized in the future? It seems like the current build system is pretty rigid, and to optimize it you'd need more flexibility. I did wonder that as well, because I thought, okay, you know, for a JITs are really effective when you specialize or you do optimizations which are more about like branching. But I think there's a quick win with this will be that the CPU will be able to use a lot of its caching. Also in the eval loop, there's a lot of jumping going on. So like each time you run an instruction, you've got to basically go back to the top of the loop and then start again. And there's a lot of instructions that happen each time. So with this JIT in particular, you can basically like compile them in sequence. So instead of having a loop, you compile the instructions into a sequence. And most modern CPUs handle that much, much better, because they're like, oh, you know, that when you do things like branch prediction, they're like, oh, I remember that one. And it can basically like cache or predict which branch to go down. CPUs are better at handling that than they are the current ceval loop, which is basically just a generic loop for all Python code. So you'll see the JIT.c program is pretty small, because basically all it's doing is copying the stencil code and then replacing the values, writing that to memory, and then marking that as something that can be executed in the future. So that's, I guess, you know, you've got these holes that then are filled in here. So I made one change, I guess, which is I just made a patch to add this function to the executor, the UOP executor, to get JIT code, so that I could actually just read the code back out of memory and then write it to disk. So this is not something that's part of the PR, but I was like, I want to see, once it's been JIT compiled, I actually want to look at it. So my little test script basically will get this test function. I will disassemble it once, call it 100 times, disassemble it again, get the executors for the test function. This uses an internal CAPI call. None of this stuff is stuff that you would normally call from Python, but I do wonder whether they're going to extend the dis module to allow you to export this. So I basically get the executor, which is this new UOP executor. And then with that, I'm going to basically write the contents of the JITted code into a raw file. So when I run this, I get this UOP executor object, and at the instruction 36, which is the little jump backwards, that one, I've got the JIT code, and I'm going to write that to disk. So that gives me this, basically what it JIT compiled was this file, which I'm not going to open in VS Code because that won't give you anything useful. But I've opened it in a disassembler called Hopper, and this is the program that it made. So we're looking at assembly code. It doesn't have, so I've been trying to work out what format this is in. It kind of doesn't, it's x86-64 because this is the instruction specific for my machine. But it's also got a whole bunch of strings in the binary. So if you look further down, you'll see all this stuff. So I've been trying to work out, I haven't quite found the answer, why they're there, because they look like the debug symbols to me. But Hopper hasn't figured out what they are. And Ada, I tried it in Ada as well, and it didn't seem to know what the hell they were. So this is the JITted code for that mini function, and in Hopper and Ada, you've got CFG mode, which is control flow graph, and that'll basically show you like what the program looks like visually. Something that struck me was that this is a big, complicated program considering it's such a tiny function. I'm not really surprised because CPython bytecodes are still really high level. But what it's basically done is it's compiled those instructions. So from here down, I guess, like these instructions, compiled what it needs to do for each one of those to turn that from a loop that needs to be interpreted into a mini program that can be run at runtime. This is my current understanding. Again, I've only been looking at this for a little bit. And you can also see when you look at the code, you'll see some of the things that it's patched. For example, we've got a call here, so it's going to call the racks register that address. So that's probably like that will be the address of the function that it needs to call, like incref or the type, for example, like a type call or something. So in our example function, we had like load const, I guess was. So let's see what load const does. Load const calls incref. So maybe that's that one. It's really hard to tell because unless you've got the symbols in this assembler, then you don't really know what it's actually calling. But those are the arguments anyway. So like most of this stuff is store things temporarily in registers, then call the function with that value. So yeah, this is basically what it's doing. Will this be any quicker? I mean, if you look at this, like, this is basically like if you took this, if you copied and pasted the body of each of these case statements for that, like, load const, store fast, load fast. If you copied and pasted each of these C values, like C instructions, put them in a program, compiled it, and replaced the args with if you like hard coded those to the actual values for this function, compiled that, and then wrote it to a program, that's basically what it's doing. Would that be quicker than interpreting it at runtime? It could be quicker because first of all, the compiler can actually make smarter decisions, but it's doing that already because it's done that generically. Secondly, the CPU can do a lot more caching that it couldn't do previously because these instructions are specific to that frame. But the important thing I think about this whole thing is that if you scroll down this template, you'll see all these like micro operations, so like binary op add with a Unicode. So like this is specific to that type. And the specialized interpreter, like once you run a function a number of times, it will say, oh, you're always calling it with a number, or you're always calling it with a string, like, and then it will replace the bytecode with one that's specialized, and then put a break in there so that if you change it, then it will go back to the generic version. But from what I understand, they're going to break these instructions down into even smaller pieces, and that means you can kind of get more specific code to, instead of just like a really generic call function, for example. And once you get more specific, that's when you can do specializations, and that's when you can make optimizations. Because otherwise you've got to call these really generic APIs like PyObjectGetItem, which is a really slow function call. Like it does thousands of things just to get the item of an object. So a subscript is where you do like something in square brackets, like that, for example, is a subscript. So it doesn't know what A is, and it doesn't know what the contents are. So like it has to do a generic lookup. Yeah, so that's basically the JIT. If you look at the PR, you can see, I guess, the important parts, which is like this JIT.c code. But when you look at it, you're probably thinking, where's the JIT? Because that's a really small program. Like, where's the rest of it? So I guess, you've got this build script, which is where some of the complication is. That's basically compiling these templates into like mini programs, and then like in the build script you'll see a reference to, actually no, in the template you'll see for my machine it stored that, it compiled that into a program in a temp folder, and then it like disassembled it and then wrote it back and described it with the holes. So yeah, it's interesting. I think if this gets accepted and it gets merged, like it'll be interesting to play with it. I think it's not going to be much quicker to begin with, but this is like the foundation of something bigger in the future, and this basically opens the door for a whole bunch of specializations and optimizations, which is just not possible at the moment. And I think we'll actually see a pretty big step jump in Python performance, either in 3.13 maybe, but probably 3.14 once this is pulled in and all of the kinks have been worked out. So yeah, go and have a look at the PR. Also on Mastodon and Twitter, I guess I've got a link to this test script and also the patch if you want to get the jitted code out of memory. Cool. All right.